Hello everyone, welcome. In this video, I'm going to do analysis of the periodic table as displayed on the screen. And I've sketched the periodic table of elements, and in this video, I'm majorly going to handle the first 20 elements. And I'm going to do analysis based on the element's name, the symbol, the atomic number, electronic configuration, valence, and any other thing that you need to know as far as the periodic table of elements of the first 20 is concerned. Now I have a display of all the elements from number 1 to number 20, which is calcium. And I really need you to understand whatever thing I'm going to explain here, because it is really going to help you in the analysis and understanding the periodic table. Now, I'm going to start with the symbols. Hydrogen is number 1 in the periodic table, and it always has a symbol capital H. Hydrogen has a symbol capital H. It has a symbol capital H. Helium has a symbol He, capital H, small e. Lithium, capital L, small I. Beryllium is capital B, small e. Boron is capital B. Carbon, capital C. Nitrogen, capital N. Oxygen, capital O. Fluorine, capital F. Neon, capital N, small e. Sodium, I'm going to skip sodium a little bit. Then magnesium is M, G. Aluminium is A, L. Silicon is Si, capital S, small I. Phosphorus is capital P. Sulfur is capital S. Chlorine is capital C, small l. Argon is capital A, small r. Potassium, I'm going to skip it a little bit. And calcium is capital C, small a. Now, those are the symbols of those elements. And before I move further, why do you think I skipped those elements? Now, let me explain something before we move. Elements in the periodic table have their symbols driven from either their English name, or their Latin names. So whenever we are coming up with a symbol, a symbol can either be first letter of their English name, or first and any other letter, of their English names. So for example, carbon was capital C. Oxygen was capital O. Now, if we move further, nitrogen was capital N. So, these are symbols driven from the first letters of their English names. First letters of their English name. But when I come back to the other elements, for example, let's try and have a look at an element. For example, beryllium is Be. Beryllium is Be, as shown here, meaning Be was driven from the first two letters of its English name. That's beryllium. I'm going to wrap that. Then, if I come back to magnesium, was Mg, and it was driven from the first letter. It was driven from the first letter and the third letter. Aluminium was Al, first letter and second letter. Silicon was first letter and second letter. Phosphorus was first letter. All the way down, chlorine was first letter and third letter. Argon was first and second. Potassium, I'm skipping. Calcium is second, first and second. So we've come to realize that an element's symbol can be driven from either first letter and second letter, first letter, second letter, or first letter and third letter. You really need to know that. So, if that is happening, what are the things that we need to know? Certain elements have their first letters or their symbols driven from their Latin names. So, that one means that certain elements in the periodic table have Latin names. That's what I wanted to say. They have Latin names. And if now I go back to whatever thing you are doing, yeah. Now I go back to whatever thing you are doing. So as far as Latin names are concerned, certain elements have their Latin names. So I'm going to discuss an element, English name, its Latin name, and how symbol was driven. For example, I skipped a certain elements I skipped, and the first element I skipped was sodium. So, and the next one was potassium. So the English name is sodium. Sodium is the English name, and potassium is the English name. Now, there are other elements. For example, lead or lead, mercury. Now, these elements have their Latin names. These elements have their own Latin names. Now, this Latin name for sodium is natrium. The Latin name for potassium is kalium. The Latin name for lead is plumbum. Mercury is hydrogen. Now, these are just examples of certain elements whose English names also have Latin names. And from those their Latin names, that's where their symbols were driven from. There are other elements, but these are the most basic elements that I want to start with. So, these elements' Latin names were the ones that were used to drive the symbols. Now, the symbol for sodium is Na. Potassium is K, capital K. Lead is Pb, capital P, sorry, small b. Mercury is Hg. So, having known this, I can now go back and fill my table, having explained that. Now, I can now go back and fill my table. So now sodium is capital N, small a, which was driven from nitrogen, and potassium is going to be capital K. Now, I have my symbol column filled. Now moving to the atomic number. As I explained earlier, atomic number is just the number of protons found in the nucleus of that given atom, forming that element. So we just number it from 1 to the last one. So for this, hydrogen is 1, helium is 2, we just list them that way all the way down. And lastly, our calcium is 20. We just list it. As far as the atomic number is concerned, we list it from 1 to the last one, which is 20. Now, before I move to the electronic configuration column, there's something also I still want to explain. I want to explain another thing that is very key. So I'll erase this area. I'll rub this area because I want to use it. I'll try to rub this given area because I need it to explain a certain concept here. Sorry. Now, after erasing that given area, let me explain something as far as electronic configurations are concerned. Now, before, as I was discussing structure of an atom in my last video, there's a concept that I wanted to explain here, so I ignored it there. Atom has a nucleus and shells. So this is going to be the nucleus, and these ones are shells. Within the nucleus, we have protons and neutrons. Within the nucleus, we have protons and neutrons. Within the shells, I have electrons. And I said in the previous video that protons are positively charged, neutrons have no charge, and electrons are negatively charged. As far as capacity is concerned, now that one is based on electrons. The first shell after the nucleus, immediately after the nucleus, has a capacity of 2 electrons. The second shell after the nucleus has a capacity of 8 electrons, meaning the maximum number of electrons it can contain is 8. The third shell also has a capacity of 8 electrons. Etc. Now, each shell can never be completely filled if the shell before it is not filled. So that's the principle behind the electronic configuration. Meaning, in electronic configuration, we want to see which number of shells are filled, or which number of shells will that given atom of that element have based on the number of electrons it's having. The next thing that I want to say is that as far as for an atom, proton number is the same as electron number and this is the same as atomic number. So meaning, if an element has 1 as its atomic number, meaning it is having 1 electron. If it is having 2 as its atomic number, it is having 2 electrons. Why am I saying so? We have atoms and ions. An atom is a ground state, that given type of element, atom, before it reacts by either gaining or losing electron. But after losing or gaining electron, it becomes an ion. So, for an atom that has not undergone reaction, the number of protons equals the number of electrons. So, when we come to that, we are going to say now that electronic configuration is always given a 1, 2, 2 to 8 configuration. Now, let me also explain another concept before I forget. Now, another concept that I want to explain is that why do elements react? Elements react to attain stability. They do so by either losing or gaining electrons. An element is only stable when its outermost shell has maximum number of electrons, has maximum number of electrons. Meaning, if it is the first shell, it must have a maximum of 2. If it is second or third, it must have a maximum of 8. So that's why elements react. Okay, that's what I wanted to explain in that bit. So let us go back to our electronic configuration and see how I'm going to fill it up. Now, in the electronic configuration column, this is what I'm going to do. For hydrogen, I'm going to put 1. For hydrogen, I'm going to put 1. For helium, I'm going to put 2. For lithium, remember, now we are on the 3rd electron, and the first shell has a capacity of 2. So meaning the 3rd electron must move into the 2nd shell. So for lithium, it is going to be 2:1. For beryllium, it is going to be 2:2. Boron, 2:3. Carbon, 2:4. Nitrogen, 2:5. 2:6. All the way down, 2:7. Then for neon, it is 2:8. Now, this was our first shell. This is now the second shell reaching its maximum number of electrons it can contain. Meaning, when we move to the next element will have now 3 shells. And we are going to write it this way. It is going to be 2:8:1. Now we are now on the 3rd shell. 2:8:2, 2:8:3, 2:8:4, 2:8:5, 2:8:6, 2:8:7, 2:8:8. Now our 3rd shell has reached its maximum capacity. Now we move to the 4th. So it is going to be 2:8:8:1. Then 2:8:8:2, which is calcium. Now, that's the explanation as far as electronic configuration is concerned of an element. Now, I'm going to move to a concept known as valence. And let me wrap this area, this region here. I'm going to wrap this region for me to get enough space for my mouse is misbehaving. I can just use this space here. Yeah, that's the beauty of computer. Now, a valency is the number of electrons an element or an atom loses or gains to become stable. And I said elements react to gain stability, and the stability whereby the first shell is complete, meaning it will have 2 maximum number of electrons in it, is known as duplet rule. In a situation where the second and the third shells is completely filled, they'll have 8 number of electrons. This rule is known as octet rule. Octagon. Oct means 8 and dupe means 2. So for that matter, valency is the number of electrons an element loses or gains to become stable in a reaction. Now, If an element, now before I move to that, let me do an analysis here. And I want you to know something here. Now, before I even move to valency, this is the analysis that I'm going to give you. Let us now analyze the periodic table. And I want you to see how I'm doing the analysis here. If an element electronic configuration ends with 1, 2, or 3, that element reacts by losing electrons. So I'm coming to my periodic table all the way down on the electronic configuration column. Then I'm going to look at this one here, and this one. Those are the ones that ends with 2 to 1, 2 to 2, 2 to 3. Then I'm moving again, 2 to 8 to 1, 2 to 8 to 2, and 2 to 8 to 3. Next, I'm moving to 2 to 8 to 8 to 1, 2 to 8 to 8 to 2, and 2 to 8 to 8 to 3. All these, what do? They react. They react by losing electrons. So I'm also moving to that given section also, and I'm going to do the same. I'm going to do the same for that. These ones also, what do? They react. They react by losing electrons. I'm still moving. I'm on this area. Let me have this space here so that I can have somewhere to write. Now, these ones also react by losing electrons. Now, for those that have completely filled shell, meaning those ones that have 2, 2 to 8, and 2 to 8 to 8, with them they are stable. With them they are stable. So 2, sorry, my battery is low. You connect it to the charger immediately. Now, these ones that have 2, they have completely filled shells, so they are stable. So this one is stable. 2 to 8, there's also another one that I'm looking for. 2 to 8, this one here is also stable. 2 to 8 to 8, this one here is also stable. Now I'm moving to the next one. Any elements or element whose electronic configuration ends with 4, 5, whose electronic configuration ends with 5, 6, and 7. So for that matter, I'm coming back to this area here, meaning ends with a 5 to a 7. This space here, that space there. So what happens is it will react by gaining electrons. So all these, they react by gaining electrons. Let me use a different color. React by gaining electrons. I'm also moving to the last bit, this region here. It is this region. 5, 6, and 7. All these, they also react by they also react by gaining, they react by gaining electrons. They react by gaining electrons. Now, I skipped 2 to 4, this one here. I also skipped 2 to 8 to 4, and only those. So meaning this one can gain or lose. Can gain or lose in a reaction. In a reaction. This one also can gain or lose in a reaction. What is going to determine how they react is the environment they are found. If the environment dictates that they give out, they'll give out, or meaning they'll lose. If the environment dictates that they gain, or there is excess of electrons in that environment being donated, they'll pick the electrons. So sometimes you can call them polar elements. Okay. Now, this is analysis of the periodic table. Now, the next thing that I want to say, any element that react by losing electron is a metal. So go back to your analysis. This one is a metal. That group, the 2 to 1, 2 to 2, 2 to 3. Any that reacts by losing 2 to 8 to 1, 2 to 8 to 2, 2 to 8 to 3, they are also metals. You go to 2 to 8 to 8 to 1 and 2 to 8 to 8 to 2. All these also are also metals. I'm sorry, this video is going to be long a little bit, but you have to bear with me because I have to give you all the details you need as far as periodic table is concerned. Now, any element that reacts by gaining an electron is a nonmetal. Any that reacts by gaining, this one is a nonmetal. So that's how we can determine the nonmetalness or metalness in the periodic table, even without going or worrying about how you can come up with it. Now, any that reacts by gaining electron, this one is also, sorry, this one is not supposed to be a nonmetal, so I'm supposed to write it here. Yeah, these ones are non-metals. So I have those non-metals. Then I have also this group. These ones are also reacting by gaining, so they are also non-metals. Do we have any other non-metal? No. Now, because most of the time, those that have 2 to 4 and 2 to 8 to 4 can react by gaining or losing, their state doesn't really matter most of the time, but when they react, they can either form non-metals or they can form solids or liquids according to the reaction they are involved in. Now, having known that, This last bit that I want to explain here. For an element to react, that given element is reacting because if the bridge is 2 to 4 and 2 to 8 to 4, any that is below this, meaning I'm talking about 2 to 3, 2 to 2, and 2 to 1, these elements will tend to lose electrons because the energy required to gain is too much. For example, if I'm having a situation whereby, for example, let me explain that shortly. If I'm having a situation whereby an element has electronic configuration of 2 to 3, for example, if I'm having electronic configuration of 2 to 3 and 2 to 6, I want us to compare this. This one needs 5 to reach 2 to 8. This one needs 2 to reach 2 to 8. 2 to 8. Now, another one can be 2 to 1. This one needs 7 to reach 2 to 8. So, under certain circumstances, an element that has 2 to 3 electronic configuration needs a lot of energy to gain 5 electrons. So, it will rather lose the 3 to have a 2 to 0 rule, which is a duplet rule. And an element that has 2 to 6 cannot lose the 6, but it would rather gain 2, because losing 6 will require a lot of energy. So it will gain 2 to become stable. So the number of electrons an element either loses or gains to become stable is its valency. And that's the last stage that I'm coming to. So for one, hydrogen always has a valency of 1. Now, this one is stable, so it has a 0 valency. This one has a 1, 2, sorry, supposed to put it here, 2. This one has a 3. Now, this one has either 2 or this one needs 4, can lose or gain 4. This one needs a 3, this one needs a 2, then 7 needs a 1, 8 has a 0 valency because it is stable. This one has 1, 2, 3, 4, then we drop again, 3, 2, sorry, let me write it where it's supposed to be, then 2, then lastly we have 1, then a 0. We start again, 1, 2. So if you look at the valency very well from element 1, which is hydrogen, all the way to calcium, so we are having a 1, 2, 3, 4, then a 3, 2, 1, 0, then we start again, then 1, 2, 3, 4, then we drop like that. So this kind of configuration is always a increasing, a dropping, increasing configuration. So that's what we mean by the word valency. So it's just the number of electrons and elements either loses or gains to become stable in a chemical reaction. So you needed to know that. You really needed to know that. Now, that's what I was having. That's what I wanted to present here as far as valency and analysis of the periodic table is concerned. Thank you very much and have a wonderful time.